I missed it. Is that for
Yeah.
Sorry about before, but I was trying to organize my thoughts about make sure. Yes, you can pass around this. Somebody, are you also getting stuff to give her handout?
I can, yeah.
Please pass them around.
Oh my gosh, just literally.
Oh, fuck. Damn. That's a spread. Someone call that out. Did you get the first question? He must have waited for the first one. People are just
That's like whatever you want to think.
I don't know enough to like say the other one. Just don't know after the first person.
Are you serious?
No.
Actually,
Oh yeah,
I just need to be I guess you at least gotta see. I mean, yeah. Like that's maybe that's Simon?
Simon. There is no Simon. Alex Girl. Matt is not here. Just over. Results as a class. So I was like happier this time than the first exam. Of course, not everybody gets very high grades. Now, those on the third column, if you have like an average, like this top, this would be a C plus, this would be C's, average, like overall average. This would be C minus, I don't know, right, maybe C minus, maybe D plus. I will have to make a judgment when I see the overall picture. These are, you know, B minuses. You start getting into the B range here. Those are not really, again, when I do the average of the class, the average of the class, I'm going to spread it out and it's going to look something like this, right? So at that point, if I don't have a 79 or 78, I might say, and if there is, if it's not so gradual, in other words, if there is a couple of people who get 76.5 and then there's a drop of 74, those might get a B plus, right? In other words, I'm not fixing myself. I'm fixing myself to a minimum for sure, right? So 63 would definitely be a B minus, but so might be 68, I'm not sure yet. And the same thing with this, right? So it is highly unlikely that there is going to be 2 or 3 people getting something in the high 90s. If that did happen, then the 85 might actually be an A minus, might, right? If nobody gets like an average that is in the high 90s, an 85 would be just a regular A. And so sometimes I have a hard time deciding where to cut off the A minus. Okay, so I'm giving one more chance to somebody, a challenge rather than chance. It has happened in my career as a teacher here about 10 times, about. And I do that every time. The final is going to be comprehensive. So, if your average right now is this, or lower, and you come in the final and you get this, you know what? You have an A in the class. If you get one of the highest grades in the final, like a very strong A, no matter what happened before, I will not even look at it. I will enter your grade as A, right? It doesn't happen every year, because I've taught here, this is my 37th year. It's happened about 10 times. Hopefully, it will happen this time. Not necessarily somebody here, but somebody would be like in the B range. And similarly, let's say you don't quite get, a very strong A, like something in the 90s in the final, but you do get the third highest grade or the fourth. Again, I will give that much more weight than originally promised or originally scheduled or described in your study. Okay. So you get one more chance. The final is going to be comprehensive. It is scheduled for May 9th, I believe. May 9th. What is the time? I think 1 o'clock, 1 to 5. Does anybody have an exam after that? After 5, like 6 o'clock. So if nobody has an exam after 5, I'll be here. No. And again, I'll give you much more time, if need be. If I say it will be like the previous exams. If I say that all the class wants more time will be given. Right? Than the 4 hours. Okay, now, going to be doing today and the next, I suppose, three more classes. It's today plus 3 more classes, right? It's going to be material without homework. The equivalence of this material will be what happens with the last material that I did for the second exam. And then you had a sizable part in your exam based on that material. The same thing will happen with what we're going to be doing right now. In other words, it could be that up to 30% of the final, I'm not saying it's going to be 30, maybe 20, is going to be on these last 4 lectures. Okay? Which means, if you don't understand it, ask questions. If you do understand it, review it so that it sticks in your mind. What we're going to be doing is heat and mass transport. Transport phenomena is fluid mechanics, but it's also heat and mass transport. I want to make sure that this is the table with the loose top. We all know a couple of things, and your experience dates back to when you were almost a toddler, perhaps. You touched something that was hot, and you felt the heat, not necessarily a hot plate. It could be a hot car, a hot seat, or something, right? So everybody relates to that. Now, I'm going to ask the following question. If my finger has a certain temperature, and this has a different temperature, and I touch it, what is going to be the temperature between my finger and that finger where they have contact? It's going to be the same, right? Now, it doesn't mean that the bodies are going to have the same temperature. In other words, if this is a cold body and I'm a hot body, and I touch it, it doesn't mean that my temperature here will be the same as the temperature there. Just where the two are touching. How do we call the area where those two things touch? Loud? Excellent. Interface, right? Interface. Very impressive. Interface. The interface between two things that touch is where they touch. Usually that interface mathematically is described as something that does not have a volume. It's just an area. In other words, if this is touching that, this area that was shown here is the interface. Sometimes the interface doesn't have to be plane, it can be like it can be circular, the interface, kind of like spherical. Do you understand these things? Remember, if you don't understand, you have to ask me, right? Okay, so we're going to take a slab that conducts heat. And again, when we have something that conducts heat, and it's a heat conductor, it's different than an electrical conductor. So something can conduct heat or it can conduct electricity or both. Usually metals conduct both heat and electrical current. Therefore, when we say something is a conductor, a solid is a conductor or a liquid, or even a vapor, we have to specify that it conducts electricity or, depending on what problem we're doing as engineers. If something does not conduct heat, we call it how?
Insulator.
Insulator of heat, right? A thermal insulator, not an electrical insulator, because you can have an electrical insulator that actually conducts heat. It's possible. So, we have heat conduction. We're going to have a slab, and we're going to set a certain temperature here, because we touch it on something that has a certain temperature, and then we have a different temperature on the bottom. In other words, you can imagine this slab, let's say, floating on a liquid that has ice, pieces of ice, which makes the temperature on the bottom what? 0 degrees Celsius. But on the top, we put something very hot so that we maintain the heat at some different temperature. So we're going to have T1 on the top, T2 on the bottom. Y is going to be the thickness or the height of this slab. So this slab is like this, right? Okay. One temperature on the top, one temperature on the bottom. I think you have been told several times in several of your courses, and you did not need to be told that, you knew it, that heat goes from something that is hot to something that is less hot, right? Which means that heat is going to be transported now from the top to the bottom, because we have chosen T1 to be greater than T2. And then you can have an experiment where you are, it's called calorimetric experiment, where you are measuring how many calories per second are entering your bottom, because that's where they are going, right? They're going to the bottom because that's where the lower temperature is. And if you did this, you would find that the calories that are entering the bottom per second are going to be proportional to how large this thing is going to be. In other words, if it is this, if the area, the total area, is not what you have on this tabletop, but on this, you're going to have much less heat. And of course, you know that because when you use hot plates, if it is smaller, the hot plate, you cannot really put a big pot and cook, right? You need a hot plate that is bigger, pretty much the size or close to the size of the hot pot, of the pot that you are putting on it. So you know that it is going to be proportional to the area. Yes?
Is this the area of the,
This.
what's receiving the heat, or the area of what's?
The area that is in touch. All these areas.
Okay.
All these areas. And remember, we have a slab here, so the area is the area of the tabletop thing, or the bottom. So the top or the bottom of what we see there. Then another thing that they found experimentally was that it is proportional to the difference of the two temperatures. In other words, the greater the difference of the two temperatures is, the more calories per second you are going to be. And you also know that. How do you know it? Because you turn on the knob for your hot plate, right? To raise the temperature, because then you heat your water faster if you turn it higher. Okay? And then it is inversely proportional to the y, to the distance. This experiment was done some time ago by Fourier, and therefore it is known as Fourier's law. But if we take the area to this side, then we have calories per second per centimeter square. And what do we call calories per second is heat flow rate, but calories per second per centimeter square is known as heat flux, because it's per unit area through which the heat is transported. Which means you have a Q, small q, and we call this heat flux, and has those units, calories per second per centimeter square. And now, one thing that we know is we want to also write this as a derivative, Fourier's law. And if we are going now to write something that we're going to call, guess what? A temperature profile, where we plot temperature as a function of distance y, small y, right? This is lowercase y. And this is 0, and this is y, capital Y. If we set our small y being equal to 0 here, and small y being equal to capital Y on the top, then on the bottom, at 0, we're going to have T1, and on the top we're going to have T2 as our temperature, which means that our temperature profile is going to be like this. Have I inverted them?
Yes.
I think T2 is the smaller one, right? T2 is the smaller one, T1 is the bigger one. You see that? So the slope of this, by the way, let me make one very general statement which has few exceptions, very few exceptions. In your curriculum as engineers, everything that you learn is going to be used in the future, including in future topics. So if you know very well fluid mechanics, you can appreciate heat transfer much more. Okay? And you will see how that is going to be, because the thinking is very similar. Now, if I take this derivative here, is this derivative a positive derivative, a positive slope, or negative? It's positive. But I have a problem, because if I draw my y-axis this way, and I want to know the rate at which heat is going upwards, and I have a positive slope, I have to put a negative sign, because I know that actually heat is going downwards, right? So if I'm going to write my law as this is equal to some proportionality constant k dt dy, I have to put a negative sign in front of this. This proportionality constant, by the way, is known as thermal conductivity. Okay? So this is again also the expression of Fourier's law using a derivative, using a sign that shows the direction towards which heat is being transported. If we had chosen the top to be our beginning, in other words, y is equal to 0 on the top, and small y is equal to capital Y on the bottom, which meant that y grows this way, and then we tried to plot the temperature profile for this. What we would have would be temperature as a function of y. This is 0, this is capital Y, this is T2, smaller, T01 is greater. But actually this time, our plot would be like this, which means that this is a negative slope, negative derivative. Which means if dt dy is negative, and we know that heat flow takes place from up, going downwards, is it a problem?
No, it's not a question. Why is it VE for the slope?
V, no, there's no, this
No,
is,
no, I know, but why is it?
Negative.
No, I know, but why is it VE?
No, it's like a
oh,
negative. sign.
nega,
Oh, negative. Yeah, I feel you.
negative. Okay. Yeah, if we put positive, that's, okay, sorry, my, okay, shortening, right? Like many times, transport, people write it like this. Export, but this is not correct, right? Because it sounds like export, but many times professors use export for transport, right? Trans, okay. Okay, so do you understand Fourier's law? All right. Now, we're going to describe another law. And that is a law of mass transport. Yes.
One quick question. So K varies for different materials, right?
Yes, of course, bless you. Yes, of course. If you have something that conducts faster, in fact, the rate at which heat is being transported is proportional to the K, to the thermal conductivity, right? And I'm not, let me say this, since Cole is taping this lecture, I'm not at all adverse, if you like, to tape all of them, not just for Tiffany, always, because like I said, these 4 lectures are going to be extremely disproportionately big part for the final. It will not just be like 5%. But 2 weeks out of 14 is not 5% anyway, right? It's more than, it's about what? It's close to 14%. Yeah, 14%.
Does K only take into account the conductivity of the, whatever you're trying to transfer?
Yeah.
So you have
Like wood has very little conductivity, would be very small. Iron would be very high.
But if you had if you had something that, like an iron slab that was hot, and you had a wooden slab that was cold, and you're trying to get a wooden slab, would that K constant consider anything of the source?
Okay. So, let's go back here. On the top you put an iron slab. On the top you put an iron slab. This is a wooden slab that has very little conductivity. What I have described is just for the wood. I don't care about the iron. The iron just gives, like, let's say, if I have a hot iron here, plugged, literally, an iron that you use to iron your clothes, and has a certain temperature, and just huge one, right? So that it touches the whole surface here. That is just going to provide the T1 on the top, that's it. The equation is written for, not for what generates energy, but for the medium through which heat is transported.
So if you have, like say if you had on a glove and you touched a hot plate, are you calculating the heat transfer from the hot plate to the glove or the hot plate to your hand? And would that be?
And we are not talking about gloves here. Do you understand this?
Yeah.
That's it. Yeah, that's a problem. What you are describing is a problem that somebody might have to deal with, you will not. Okay, that's it. The glove is more like an insulator. Okay, do you understand this? Okay, yes.
So are the T1 and T2 on that graph the same as the T1 and the T2 on?
Absolutely yes. Absolutely yes. Right. That's why we get this negative, and the other one is positive. The other one is positive, right? Slow.
So I guess so on this graph right here, we're saying that at the top,
Okay,
y
on
is equal to
this,
0.
on this graph, we have a negative slope, right? We know that heat is going this way. So if I write this equation and I don't have a negative sign, I'm showing the opposite of what is really happening. So the negative sign is always part of the equation,
Okay.
right? This explains why the negative sign is always part of the equation. By the way, you realize that this is very similar to Newton's law of viscosity, right? Okay, now, next experiment. Again, this is a slab, but it is like this material. Do you like to press it, or do you relate to this material? It's a spongy material. So imagine this slab being spongy, like this. So, we do the following experiment now with this slab. We take a beaker or a big container and we place it like this so that this spongy material divides liquid on the top and liquid on the bottom. Can you imagine that? This dividing, so the tank is exactly this circumference that has this. So it goes up like that, and below. Below it there is liquid, on top of it there is liquid, and inside it there is liquid. Okay? In this experiment, the liquid that we have on top is going to have some red dye. Of a certain concentration that will produce a certain molar concentration right on the top of this spongy. So if this is the top, do you see the top? This first layer of sponge is going to have a certain concentration of that red dye. So, since we're talking now about molar concentrations, we're going to have C for concentration, will have moles per volume. And we impose on the top a concentration C1. On the bottom, we can have a system in which we can have like a liquid that is moving so that we maintain also a constant concentration on the bottom, C2. Right? So the bottom concentration could be 0 if we have this water flowing out. Right? Flowing so that we don't, if we look at it, it doesn't look any red at all. But if it looks pinky, so this is like blood, right? Red. This to the eye looks like pink, this water here, which means this concentration is greater than this concentration. So we're going to have C1 greater than C2. So there is going to be flow, of course, of material. The dye is going to be diffusing. Huh? What?
My AI.
Okay. Okay. All right. So again, if we want not the calories, please pay attention. If this thickness is capital Y, okay? So it happens by chance that this thickness is Y, capital Y, from here to down there. If we change like moles per second per centimeter square, it actually happens to be C1 minus C2 over Y, proportional to. And of course, there is a proportionality constant. Once again, if we wanted to write now this, and we're going to call this flux, we're going to use for molar flux the letter J, molar flux using the letter J is going to be equal to negative script D dC dy. And this script D is going to be known as the molar diffusivity. And this is somebody else's law. His name was Fick. So it's Fick's law of diffusion. Fick had two laws, first and second, so not usually this is referred to as Fick's first law of diffusion because there is another one. Okay? Fick's law or Fick's first law of diffusion. Are these things clear to you? You've heard something like that before, right? In some physics course or not? No? Never? That's fine. I'm teaching it as if though you've never heard of these things. Okay? Okay. Now, problem. That's the problem. When you have light, you have light because there is electrical current being transported through an electrical wire. And electrical wires, you probably know already, are cylindrical most of the time. In computers, actually, you can have wires that are not cylindrical. But wires, like the ones that we're using in houses, are cylindrical, or cables. And you probably, hopefully you don't know anybody personally, but you must have heard that there was a fire in this house and the house burned down to the ground because of an electrical wire problem. What did they mean by that? They meant that as electrical current was going through that wire, the heat that was produced inside that wire did not dissipate, did not escape to the surrounding, to the ambient fluid, which usually is air. It accumulated there inside the wire, and the wire got hotter and hotter, it melted down, and it started burning things around it. And then that fire expanded. It's much more common than you would think. Okay, because almost, well, not all, unless you have arson, somebody doing it on purpose, most of the fires are caused by electrical wire failures. Which means that if there is heat generated inside this wire, you want this heat to go out of the wire and leave your wire. And you can specify that in order for that to happen, through a different problem that we're not going to deal with in this this semester, perhaps you may or may not deal with it next semester in Transport 2, you have determined that this wire is gonna work well if it operates with a surface temperature, let's say, of if the ambient temperature is 25 degrees, maybe 28 degrees. So that when you touch it on the surface, it's not going to be too hot. Because if you touch it and you burn yourself, it means that there's going to be a meltdown. That's how we call it, meltdown, because that's when the problem happens. When the metal, out of which usually copper wires you have mixed with something else, an amalgam of copper and something else, when it reaches a certain melting point, it melts down and then it melts other things around it. That's when you have the accident taking place. So you want to specify a certain temperature. So you want the air around the wire to be able to absorb this heat calories per second that's being generated and it's coming out of the wire. And you want to ask the question, the engineering question for you, that you will be able to answer today and in your exam for sure, is when this wire is not like this, but when it is like this, how many calories per second are coming out of that wire, right? And that wire could different, go all around the walls and everything. So that's a question that you will be able to answer in minutes. Of course, if I started teaching you that stuff 3 months ago, it would take maybe a couple of lectures to answer it, because you did not know fluid mechanics. Okay. Now, you have seen probably in your physics course, perhaps physics 2, that the rate of heat generated is related to the resistance, the electrical resistance, and the current that goes through. The higher the current. But we're not going to deal with electrical currents here. We're just going to say that for this, how much current is being used right now, is being conducted, is being transported right now to light up the room, there is a certain heat that is being generated inside that wire. This has units of calories per second per cubic centimeter. In other words, the electrical engineer has done the job and has told you this is the heat generation. Actually, a chemical engineer can also do it. Right? That's why you take circuits in physics to be able to do that. So we assume that we know the so-called S, or generation term. Generation. Heat generation. And this is going to be considered as a constant. Remember, it's going to be different. Please pay attention. When you have a wire that brings electricity to this room, it's going to be different now than now, right? You carry less current, therefore you're generating less heat now than after I have turned on these lights as well. But we're going to be considering it constant. We will not consider, turn on, turn off lights and stuff like that. We have the lights on. Okay. All right. So what is it we're going to do? We're going to do a heat balance, energy balance, also known as the first law of thermodynamics for a closed system. A Okay, what is going to be, in order to do the first law of thermodynamics for a closed system, we have to define what the system is. What is the system going to be? Look,
In what case?
for the wire.
Up to the wire? Just the
Okay, we could actually also do it that way, but it's not as nice. So if the wire is cylindrical, we will consider within the wire a, say it? Yes, an angular shell, this. Right? Because we know fluid mechanics. So if our wire has a radius capital R and a length L, just like we're going to look at it just like the tube through which it was flow, we're going to select this. That has a thickness delta R, a length L, and it's chosen at a small r. How do we call the small r? Radial position, or right at radial position, which is different than the capital R, which is the radius of the. And remember, we have set the temperature T0 on the surface. So that's like the requirement. The surface temperature is going to be T0 because the room is 24, 25 degrees. The wire is going to be like 30 degrees, and that's our T0. Okay. I'm going to redraw that the system. What is this? And we write the law, the first law of thermodynamics that says du dt, which is internal energy accumulation, is equal to the heat, the summation of all the heats that go in and out, plus the heat generated, minus the work that's being done by the system. Closed. Obviously, this is a solid system. It's a closed system. It's steady state, which means the left-hand side is equal to what, Caitlin? 0. Very good. The left-hand side is 0. The work is going to be 0 because it's not doing any work. So this will be 0, that will be 0. So we're going to deal with the summation of the heats that go in and out, and the heat that is generated. First, let's start with the heat that is generated. Katie, it's going to be S times what? Remember, we want calories per second as the answer. Now, really? Is this area? Oh my God. It's S times the volume of the element. The volume of this. Look, what is the volume of this?
Form of that?
Yeah.
Pi r squared L.
No. 2 pi r delta r times r. Right? This is the area. And this is the L. Is this okay? Now, plus the heat that is entering at distance or position R minus the heat that is exiting at position R plus delta R. This is going to be the flux times some area. The flux times some area, lambda. What is the area? Here, look at it. 2 pi r, very good. 2 pi r times L. 2 pi r times L. And that's our first law of thermodynamics, or energy balance, for this annular, thin annular shell. Is there anybody who does not understand this? Now notice that the heat is going in like perpendicularly to the inside surface of this, right? Okay? Does everybody understand this? No. Q. Q is negative K dt dr. This is Fourier's law.
No, I mean, why is no pi r?
Okay, Q is the flux. It's calories per second per centimeter square. Right? In order to get the flow in terms of calories per second, what do you multiply the flux? By area. Well, the area, this area is this, which is 2 pi small r. You see that? This circumference, 2 pi r times L. Right? Other questions?
I'm confused as to why it's not the area at the front of the annulus, why you take the area of the entire tube.
Okay. I'm glad you're answering these questions. Now imagine that this is inside the annulus. Inside the annulus, right? So the annulus is engulfing, it's going to be chosen so that it just goes around the chocolate. The heat is generated inside the annulus, inside this, it's coming to the annulus, how? From this surface. It doesn't come this way. The heat is generated inside. Now, I know why you're confused. It's because current is moving this way. But heat is generated and then it's moving radially. It's moving in the radial direction. So, if you, please follow this experiment. This is inside the annulus. When my hand goes around, it will be the annulus. The heat from this is burning my skin in a radial position all around where I'm touching it. Okay?
Do we have like a heat profile that's similar to a velocity profile?
Yes, that's exactly what we're doing.
Okay.
It's exactly what we're doing. Okay? You can understand it now. In other words, the heat is coming in like this, is exiting like that. All around. Right? Yes.
So, if you take a point along this annular shell that we're
Yeah.
analyzing, and you were to describe a direction that heat is emanating from it, would it be in a circle or would it be like spherical, like in every direction? Like,
No.
do you have components of?
No, because the wire is cylindrical, so it's not sphere. In other words, what you are considering is that if this is the wire, the heat is coming out. I'll try to do it with my fingers, like this, right? Perpendicular to its surface.
Yes. So always perpendicular
Yeah.
to the surface.
That's right. That's right. That's exactly what actually does happen. Yes.
So no heat on the cross section.
No, because you're just taking a small part of the wire. Okay, so I think we have some wire here, right? No, this is not wire. I thought maybe this. I don't know. We just take from here to there. So if this is like the wire, it's not. If this is the wire, it goes. We don't take like the whole. We don't need to take the whole wire. We just take a piece of the wire, and that's L. Yes.
So this is again, so there's probably like end effects for.
No end effects.
Okay, so excluding end effects.
Right. Then because the temperature here would be the same as the temperature there. In fact, that is totally correct. In other words, if you have a wire that transports electricity from there to there, the temperature of the wire is gonna be the same there as there.
So there's.
So you don't consider the transport of heat this direction. Okay? I'm glad you asked these questions. Do you understand it? Alright, if you do, now, we're gonna do exactly what we've done before. Turn this into a differential equation. Divide by 2 pi, divide by the L, because those are constants. And then we're going to have that Q R R plus delta R minus Q times R at R. In other words, I'm changing the order. Minus S times R delta R, because here we have both R and delta R, is going to be equal to 0. Since you know fluid mechanics, what do you do next? Alexis? Divide. Divide by delta R, right? We divide by delta R. We let delta R take the limit as delta R goes to 0. And then we're going to get d q times r. dr minus s times r will be equal to 0. And then we're going to substitute Fourier's law for q. Just like we substituted Newton's law for velocity gradient. And when we do that, we're going to get d dr r dt dr plus s r over k is going to be equal to 0. All right? You see that? I don't need to explain it. And then we're going to now integrate. This is a differential equation. We're going to rewrite it as d dr r dt dr. Now, what is dt dr going to be at the center, at the axis? Dominic.
What's
dt dr at the center. Ni hao. Alex, Simon. Yes.
0.
Yeah.
Yeah, of course it would be 0. Because it's symmetry, right? At the center. Right? And also at the center there is no flux. So dt dr times negative q is a flux. So that is 0 at the center, because at the center you just have yeah, okay. So this is negative s r over k. This is our differential equation with boundary conditions. At small r equal to 0, dt dr is 0. At small r equal to capital R, t is equal to t0, that constant. All right? Now, this looks awfully similar to the velocity problem for a zero flow. The only difference is at this boundary condition. What is the difference? Gabrielle, do you remember? What was the velocity at the capital R?
Wasn't it 0?
0. because of no slip, right? So if we define a new term that says f is equal, defined as t minus t0, then this differential equation will be the same, because since t0 is a constant, I can easily subtract it from the argument of a derivative, because dt0 dr is 0. So here I can subtract 1 million, right? Or anything I want, so I subtract t0. This is going to be also the same. And now f is going to be 0, so that I get exactly the equation that I had for velocity. In other words, I'm going to rewrite the differential equation. Is that covering for her, this part? Okay. So dr of r df dr is going to be equal to negative s times r over k, with conditions that at small r equal to 0, df dr is 0, and at small r equal to capital R, f now is equal to 0. Next, we start integrating. Small r df dr is equal to negative s over k r squared over 2 plus integration constant. Correct? And of course, that gives us the integration constant. Stephanie, what is the integration constant? Huh?
I don't know.
Okay, so you can see that now if I divide by small r, I get this. And I know that when small r is equal to 0, df dr is 0, right? Do you see that first boundary condition? Okay? So what is C1, Stephanie?
0.
Very good. So C1 is equal to 0. This is again exactly what we've done before, right? Then second time integrating, f is equal to negative s over k r squared over 4 this time plus c2. Now we know that when small r is equal to capital R, f is equal to what? To 0, which means that C2 is simply S over K times over 4K times capital R squared, or F, which happens to be t minus t0, is equal to s over 4k capital R squared times 1 minus small r over capital R to the square power. If we remember that the velocity was delta p over 4L mu, 4L times mu or mu L times R squared, 1 minus small r over capital R to the square power. We see, of course, a striking resemblance. It's the same equation. The difference is that delta P over L is substituted by S, because mu corresponds to the K. In other words, mu is the viscosity, right? And K is the transport property for the transport of heat. Of course, we have a parabolic velocity profile. And now, if you want, you can use this equation to answer the engineering question, which was how many calories per second are being released by this wire. How you do that? Well, you do what? You take the derivative, you multiply by negative k, and you multiply by the whole area, which actually is going to come out to be something that you could have answered even without knowing any of this. It has to equal what? S times the volume of the wire, right? Because if this is the number of calories per second per cubic centimeter, if you multiply by the whole volume of the whole wire, which is pi r squared times L, you should get the amount at steady state of calories produced inside is the same as the amount of calories escaping from the wire. Which brings us back to, again, make another comparison. Remember that we know this here, the delta P over L, which is it's the pressure gradient, and it is what? It is the driving force for flow, right? In fluid mechanics. Bless you, Jasmine. It's the driving force for flow. Well, this is substituted by S because S is the driving flow for heat transport, heat conduction in this case. So the driving force for the transport phenomenon of fluid mechanics in a tube is delta P over L. The driving force for that is S, and the equations are absolutely the same. And if you remember, for the tube, one practical question was, what is the rate at which the tube is being sheared? And we said that, we showed that that rate is equal to delta P times the whole area, which is similar to what I wrote there. Okay? So I want you to digest all this extremely, extremely well, because next week's lecture is going to be much more involved, but it will be easier, trust me. If you know what we did today extremely well, next lecture will be easier. If you don't, next lecture will be impossible. There's no way you can understand next lecture. We haven't finished though, right? First, I'll give you a chance to ask questions, which I hope you will, yes.
What does F stand for again?
What?
What does F, the variable F stand for?
It is defined as T minus T0. That's why here when I solve for F, I substituted T minus T0.
Was that like an A?
No, just, actually most books don't do that. They just solve for T and they find the same answer.
Yeah.
But I wanted to put it exactly in the form that
We've seen.
you had that you've seen before, in order to drive the point that do not think, oh, I can take it easy in transport 1, but I'm gonna ace transport 2, and then and whatever other courses you're going to take. No, it doesn't work that way. Maybe unfortunately, right? happy about that, but that's a fact of life. Yes.
So it doesn't have to be electricity, right? It could be like hot water through a pipe that would work the same way. So, right?
It can be, don't think of hot water. Think of an exothermic reaction. So, I have given this exact problem, maybe even last year. So it's very good that he's thinking that way. Pay attention. So what I told them last year, I said you have a reaction a reactor, tubular reactor. Stuff is going through it, and as it goes through it, because you have reaction, you have the generation of heat. Guess what? The heat, I might have given it like a different letter, just in order to make them think a little bit, right? So I said the generation of heat from the exothermic reaction is, I don't know, R instead of S. Calories per second per cubic centimeter. The temperature on the outside of the reactor is T0, or I probably put like T1, right? It was exactly the same problem. Okay, most people did it. Some people like totally freaked out. We have not done exothermic reactions. What is this? You know, like this. So, and for engineering, this is extremely important, right? To see things and say, not be scared. You look at something that seems hard, but you can always go back and relate to something you know. Yes.
So can I probably talk about like what would you be asked to find in that?
What? In which case?
Like the exothermic reaction.
Same thing, like temperature profile, like this. Yeah, I asked them to find the temperature profile. I asked them actually what is temperature at the center, because the temperature at the center is the highest temperature, right? And I might have said, just in order to make them not be scared in the future, I might have said, well, this exothermic reaction can be a runaway. Have you heard of the term runaway reaction? Runaway is reaction like if it reaches certain temperatures, it goes wild and then everything melts down. And where you don't want to have a runaway reaction is in the nuclear reactor. That's where the nuclear meltdowns take place, nuclear reactor meltdowns, when you exceed a certain temperature, okay? So I want to know what that temperature is. And obviously, it's what? It's there, right? When R is equal to 0. Just like the maximum velocity, you have the maximum temperature. So those are questions practical questions that can be asked. Also for the metal wire, because you don't want the maximum temperature to be melting point temperature, right? You want it to be quite a bit below the melting point of the material that the wire is made out of. Any other questions? I want to give you 5 more minutes to say something.
So in this question, so we don't discuss the swallowing of the container trash due to the
No, we don't. Just what I said. Okay? I'm gonna say more things next class, and you will be responsible for those too. Okay. Now, there is another very important law in heat transfer or heat transport. So Newton was a true multi-phenomena genius, right? He had several laws in different areas. Newton's law of cooling. And it's very different than Fourier's law of heat conduction. You have also all experienced how you get, when the weather is cold, how you get warm if you are cold to something that is much warmer than you. In other words, if this is an electric heater, right? Do you know what an electric, have you all worked an electric or used an electric heater? Okay, so an electric heater pretty much is like the coil, some coil that you pass electricity through, and it becomes very warm. Actually, similar phenomenon as what we studied before, but now we're looking at something else. Actually, you may have felt that not just with an electric heater, but with your hot plate. In other words, if when you were very, very little and it was cold at home, if somebody was cooking at home, you went close to the stove because you got the heat from the stove. That's a totally different phenomenon than Fourier's law of heat conduction. That we call convection, because you get heat from something, from a surface that is solid, could be liquid, it could be a big area of water that is hot and it's giving off heat from the top, but usually it's solid. And heat is going from that hot body into the fluid that surrounds it. The fluid that surrounds it does not have to be air, it can be even liquid. In other words, that's how they heat swimming pools. They put a coil inside the swimming, the water of the swimming pool, and then that water heats up. Okay, so Newton's law of cooling says something very, very, very intuitive. If this is hotter than the air around it, please, does it make sense that to say that the calories per second that is giving off to the air around it is proportional to its area? Sure, right? The bigger the electric heater, the greater the heat that we receive into the room, that goes into the air of the room. Of course, the higher you turn on the knob, the greater the heat flow is going to be into the room, which means it is also proportional T of the surface of the hot body minus T in the bulk. And the concept of the bulk we're going to discuss. That's it. That's Newton's law of cooling. It says that the calories per second given off by a hot body to the surrounding environment is proportional to how big its area is and proportional to the change in the two temperatures. Very simple. Okay. I could have done it, I think. Right? Too bad. We could not, right? I think most of the population of the earth now, if we did not have these laws, if you ask them, they could answer it, right? But that's why he was a genius, because he came up with very simple stuff as well as more complex. Okay? Newton's law of cooling. We want to write this in a flux term, because if we take the area to the left-hand side, it's going to be centimeters square, so we always like flux. So remember, this is a different flux. So then we have T of the solid minus T of the fluid. Now the bulk, I'm going to put T of the solid minus T of the fluid instead of T of the surface. T of the bulk, they're the same thing. And the proportionality constant is going to be H. H is something that we know as the heat transfer coefficient. very different than the proportionality constant of Fourier's law, which was called thermal conductivity. Okay? So this is Newton's law of cooling. And it's going to be used by us next time. Yes.
Why is it centimeters squared instead of?
Because it's the surface area.
That's still the-
I had an 8 here.
Oh, okay.
I took the 8 to this side. Right? Yes. Okay. This is temperature of the bulk fluid. So it's the temperature really of the fluid. Not very close to the surface, right? After you yes. Close. When you get really close to the hot body, actually the temperature is higher. We'll explain that much more next class. Okay? Homework I sent anyone, if you want to give it, okay? Yeah. If you want to give it a homework, you can, right? But for most of the class, I think, because of an organic chemistry thing, is. Yeah, please leave your homework here. Yeah.